Okay, so let's see. Okay, first of all, I have this sequence for you. It's actually not in the OEIS. And it goes like this. So let's see if you can guess what comes next. So it goes Zalberger.
Those are not instruments.
Dan. McKean. So can you guess what is the next one?
Is it you?
No, it's
That
not.
was my best guess.
I know the answer, but I won't say unless you want me to.
So it turns out, well, I guess you could say.
Feller?
Yeah, so that's the speller.
Oh, we're going up.
You're going
And
backwards.
the relation is a recurrence. So this is disease advisor and so on. So Feller, I guess, is what his great grand advisor. Okay, so anyway, William Feller wrote this book on probability, and then he talks about coin tosses. Okay, so suppose I have a coin, and I toss it a bunch of times, and each time, depending on the outcome, I either win $1 or lose $1. Okay, so there's a bunch of ways you can categorize a game like this. So you can say win $1 is like walking up in your random walk. So I'm going to draw a picture in a bit. So in other words, it's like a walk in the direction 0, 1 in the plane. And then if you lose $1, that's like walking, I guess, to the right. Okay. So the point is, if you have a game, so you have a sequence of wins and losses, then you can interpret that as a random walk. Okay. So for example, so the one I have is, suppose we have a game where we win 3 times in a row, then we lose 3 times, and then we win one more time. So 2 times, whatever. So we win twice, then we lose 3 times, and then we win one more time. All right, so the coin comes up in our favor 2 times in a row, but then we have a little losing streak, and then we win one more time. So you can interpret this as a walk in 2 dimensions. So we start at the origin, and then so I said winning is like up. So here we win, and we win, and then we lose, and we lose, and we lose, and then we win one more time. So I guess I didn't draw that right. So we lose and lose. Okay, that's better. Right? So again, when I go to the right, that's like a losing time, and up is like a winning time. Okay? So we start out with 0 money, then we win $1, and we're at $2, then $1, and $0, -1, and a 0. Okay? So everyone's clear on what I mean here, right? So in particular, notice that this diagonal is like your break-even line, right? If I'm on the diagonal, that means at this particular time, I'm breaking even. Okay? So let's see. So given a walk, in other words, a game, W. So now we can think of W as just a string, right? So it's a string made of R's and U's. So then we have these statistics. Okay, so in his paper on probability, or actually his book, Feller describes a bunch of statistics. So for example, you have a certain game, you might be interested in how many times you're losing, right? Or how many times you go from winning to losing, and so on. So he defines these statistics. A1 of W, or actually the very first thing I should do is the length. So L of W is just the length of the string. So over here, let me give you that example that I drew. So in this case, L of W would be, I think it was 6. There's 6 steps. And then there's A1 of W equals number of losing times. Okay, so here you go. This is basically the number of times below the diagonal. So this counts as a losing time. And actually, we would count that as a losing time. That's the convention. So if you're losing and you go to the diagonal, that's losing. So it would be 2 in this example. And then A3 of W is the number of break even. which turns out to be 2 in this case. I guess we don't count the beginning. And okay, last one. A4W is the number of sign changes. So each time we go from winning to losing or the other way around. So this one, I guess that would be the only one. So there's 1 in this case. Right? So the point is for any walk in the plane, we have all these statistics describing the walk, right? Okay.
What's A2?
Yes.
A2? Yeah, I did it right that. So A2 would be the number of break-even, okay, right. So what did I do here? So this is, the number of break-even times he called A2. And then, okay, so the one I actually missed out was A3. So A3 equals the last break-even time. So in this case, that would be, well, the last break-even time is your very last step, which is 6. So 6 in this case. Question? Yeah.
Wouldn't A1W be 1?
Yeah, so like I said, there's actually a convention that if you hit the break-even region coming from the losing region, that's counted as losing.
Oh, okay,
Yeah,
so each
that makes
break-even
it
point is
easier.
counted as
Yeah.
half.
Yeah, it turns out that just makes things easier later on.
Okay.
But does
So-
it count as winning if you hit it from the other side?
No,
Yes.
well, I guess it doesn't count as losing, so yeah, it does count as winning. Yeah. So, that's nice. Okay, so before I do anything new, I just want to show you some interesting results from the book by Feller. So first of all, let's let Wn, let's define that to be upright walks. Yeah, okay, so UR just means you can step up or to the right. So upright walks. W such that the length of the walk is n. Okay? So it's instead of all those walks.
2 sign changes from 0 to -1 and from -1 to 0?
Right, so going either direction is a sign change.
If you wrote 1.
Right, so this is the only sign change.
Oh, it doesn't count sign change from 0 to -1?
From 0 to minus. No, yeah, this is exactly 1. So every time we cross the diagonal, that's 1 sign change. So that's just 1. Okay. And so if we define W1 as walks of length n, then there's this thing called the discrete arc sign law. Okay, and what that says is A1, I don't know, so let's say we just give that the sample space Wn. So what I mean by this is, suppose we just randomly pick a walk of length n. Then the number of losing times for that particular walk is going to be a random variable, right? Assuming, we're uniformly randomly picking a walk, right? So now we can ask, how is the distribution of this? So, and the discrete arc sign law says that this has PMF, so its distribution looks something like this. It's like a U shape. Okay? And of course this is discrete, so it's really just a bunch of dots like this. Okay? But it's limiting to a curve that looks like this. Okay? So just to make sure you're clear, again, this is the number of losing times of a walk with length f, right? So what this is saying is that if we flip a coin a bunch of times and we keep track of how many times we were in the red and we were losing, right? Then the PMF looks like this. So in particular, this is saying that for most of the walks, you're either in this region or this region, right? So it's saying like, you're either winning for most of the times or losing for most of the times. Okay? Which might be counterintuitive, right? So it's saying that if you play a particular game, you're probably either going to be really lucky or really unlucky, right? The in-between doesn't happen very often. Okay? So any questions about that? Okay. So that's the discrete arc sign law. So now let's look if you're walking to the diagonal. So that was all walks of length n. So now what if we restrict to walks to the diagonal? So I'm going to let W and N equal the set of walks to NN. Okay. And okay, so before I do that, let's see. Okay. So now we're just walking, so maybe like a walk like this. So we start at the origin, and then we end up somewhere on the line y equals x. Okay? So, I don't know, so one interesting problem is, how many of these have a1 equals 0? So what's the size of the set W such that a1 equals 0? Alright, so, does anyone remember, so in other words, how many walks go from here to here, but they never go, I guess I drew this wrong, so they never go below the axis, right? So always staying above. So in other words, you're always winning. And those are, yeah.
It's just the Catalan number.
Yeah, they're the Catalan numbers.
Disagree,
right?
it's not about the paths.
Sorry?
Thick
Right,
paths.
so there's a result that says the size, well, I guess I just wrote it, let me write it again. So the size of all W and W and N such that A1 of W equals 0 is just the nth Catalan number.
How do you define the Catalan numbers?
Which is,
Sequence 108.
yeah, so the formula for the Catalan numbers is 1 over n plus 1 times 2 on choose n.
There's a bit of a problem with the notation. WNN has length 2n, right? So it's
Right.
really, that's a subset of W2n.
Right, so maybe it's bad notation. So yeah, this is a subset of W2n. Right?
Oh, isn't that
Because they have
right?
the walk set length 2n. Right. Okay. So, right, and so like you said, this is in the OEIS, and it's A000108. And this is the Catalan numbers. Okay. Okay, so the proof of that is pretty easy. It's just a reflection argument, so I'm not going to go over that. But I mean, if you have questions, you can ask me later. But I think it's pretty common. Okay. Okay, so now let's look in general. So what if we're not interested in the walks that are always winning? What if, for example, we want the walks that lose exactly once, or something like that? So in this case, we have the Chung-Feller theorem, which actually says that we have that same result. Okay? So Chung-Feller. The size of all walks going to the point NN such that A1 of W equals 2K, or of course K can't be too big or small, otherwise it'll just be 0. This is also equal to the nth Catalan number. So in other words, this is sort of like a uniform distribution, right, of the even numbers. Okay. So in this case, the PMF looks just like uniform. Of course, you always have an even number of losing times, so on the odd cases, it's just 0. Okay. Any questions about that? Okay, so enough about this. So let's go to more general stuff now. So what if I have diagonal steps? Okay. So in other words, like what if we have a forward king? And I think these are also called royal paths. Okay. So let's let, so let's use the same notation. So KAB equals the set of all walks from 0, 0 to AB with steps. And so now we can step 1, 0, 0, 1, and 1, 1. Okay, so we can go to the right, we can go up, or we can take a diagonal step. Okay? So it's like a king, and it's like an infinite chessboard, and it moves always forward. Okay? So I think this is still, because there's still symmetry in this case, it's pretty, people study this, and so it turns out in this case we can find the generating function So let's define a generating function fe of zt. So if you give me a set of walks e, define the generating function, the sum over the walks in that set of z to the n of w times t to the a1 of w. Okay, so, and where, I should have said, so n of w, right, so now let's, okay, so for now let's restrict to that diagonal again. So we're going to the diagonal. So we have our king and he's walking and he ends up on the diagonal. And so let's define this generating function. We add z to the, where he ends up, times t to the number of losing times. Okay. So any questions on what I'm defining over here?
Wait, so
Yeah.
I don't see the n of w when you see where he ends up. I thought you said he's always ending up at nn.
Yeah, exactly. So now see I'm saying e could be any set of walk stuff.
Oh, so
maybe
they're not
we're
all
going,
k
yeah, right. Yeah, that's a good point. So I should have defined another thing, maybe k, where it's just all walks. All right. So yeah, here we go, and then we're ending up at
But
nn.
if he ends up on sort of a comma b, how do you define n of w? Or you're assuming he ends up on some point in the diagonal.
Right. So maybe I should say
But
that. So
you'd be
maybe
meaning overall n, really.
yeah. So that was bad news. So I should say maybe like k be the union of k and n, right? And then if we have e as a subset of that.
Okay.
Right. Something like that. Okay. And so now the reason we're doing this is because if we could compute this generating function, then we know how to find moments and stuff like that from generating functions, right? So we can at least have some information about the distribution of the number of losing times in this general case. Right? Okay. So what we can do is we have a statement about walks. We're going to use the fact that in a lot of cases we can convert that to a statement about generating functions. Okay. So, for example, okay, so here I'm going to put your set E, and then here I'm going to put the corresponding generating function. So just an example, if we have the set, say A union B, so we have some walks and then we add more walks, the generating function will just add. So then the generating function of this is going to be FA plus FB. Right? So that should be pretty clear from the definition. Right?
Right. You're assuming A and B are disjoint?
Oh yeah, that's a good point. So yeah, we are assuming that they're disjoint. Right. Okay, and then so in the same way, if you have A times B, or actually what I mean by this is A, so you look at all walks in A, and then you concatenate them with walks in B, right? So if you concatenate, then the generating functions multiply. And then if I take this, so this is, if I take A and I close it under concatenation, so this is A, union, AA, and so on. All right, so if I take, this is the clean star of a set of walks, and then I close that under concatenation, right? So that makes a bigger set of walks. It turns out that the generating function for this is just, so.
How does the union of walks look versus concatenation?
Concatenation, you do one and the other.
Yeah, you take one and you add it to the end of the other one. So if you think of strings, it's concatenation of strings, right?
Yeah, but then when you union them together, are these sets or are these individual walks?
Yeah, these are all sets of
Okay.
walks.
But how do you concatenate two sets? Do you look at all pairwise concatenation?
Right, yeah. So
Okay.
it's pairwise concatenations. Yeah. Yeah.
Does that last one also assume that like A and AA are disjoint?
Yeah, it would. Well, I mean, are they automatic? No, I guess they're not. Yeah, so, but it does, I guess it would assume that, yeah.
No, it doesn't matter.
Does it? I don't know. What?
No, the union's not going to change.
Oh, yeah, I guess you're saying about this though, right? Will this be true?
I feel like you need like an empty walk in A or something for that to be true.
Okay. So I don't want to waste too much time, but let me just say that. So the calculations we do, all these work. Right? So you do end up with that. Okay. Maybe in general it's not true though. I got to know that. So the reason I wrote down all this stuff is because we can say this. Let me write it over here.
You could write A plus B instead of A union B. I don't think they have to be disjoint.
Okay, so let's see. So we have any forward chain walk, and let's suppose it's ending on the diagonal. It turns out it's always going to be of this form. Okay, it's going to be some diagonal steps followed by what we could call like a negative walk or a positive walk, right? I'm not going to draw it too well. And then followed by more diagonal steps, and then followed by either a negative walk or a positive walk, and so on, right? So we go along the diagonal, and then maybe we walk below it a little bit, and then we go on it again, and then above it, and so on, right? So it's a repetition of things like this. So each section, if you break it up, each time we hit the diagonal, it's going to look kind of the same, right? So we have a statement about what a forward chain walk will look like. And so we can convert that into an algebraic equation with generating functions. Okay. And so we have this f. So again, this just means all the walks. Right? So we have this as an algebraic expression in terms of whatever, z and t. And of course, I'm not going to write it down because it's, you're going to have a bunch of equations. You solve those with Maple, and so you get an algebraic expression involving z and t, square roots and stuff like that, but it is closed form. Right? So, any questions about that? Yeah, I'm definitely not going to go over it, but if you have questions, you can ask me later. So, and the nice thing is, so once we get this, right? So remember, this is the sum of z to the, where we end up, times t to the number of losing times, right? So then you can use this. If I fix n, right, you can just use some Taylor expansions, and you can find the distribution of a1, okay? And so then you can find what that random variable looks like, right? So for example, if I say, my chain is starting here and it's walking to the point 10, 10 or whatever, then you can say the number of losing times is a random variable, and we know the distribution of that, right? Okay. Yeah.
So if I'm in losing land, then I go up to the diagonal, so that counts as a losing time. But then if I stay on the diagonal for one more step, does that count as another losing time?
Actually, it doesn't. Right. It doesn't.
It's okay.
Using our convention, it's just, I
Just
guess
when you
it's
go
sort
up
of
to
neutral. Right. Yeah. Okay. So, okay, but we don't know the moments as functions of n. Okay. So distribution, right? So you have a distribution, the moments sort of make like a fingerprint, right? So you can find the moments, you're good, right? In this case, we cannot find the moments as a function of n. Okay? So if you give me a particular n, I know the distribution, but if you want to say find the limiting distribution, we don't. Okay? And so the reason I'm saying this, I probably should have said this before, is in the Catalan case. So when you're going to n comma n, this chunk color thing, we actually can't find the moments as functions of n. Okay, so let me show you. So back to W and N. So we know the moments of A1 restricted to W and N as functions of N. Okay? So for example, the expected value. Okay, so this is, if I'm walking to the diagonal, what's the expected number of times I'm below the diagonal? Well, just by symmetry, we would expect it to be like half, right? So half of 2n would be n. So we know that. And then, so it turns out you can use, so Maple has like a convert to formal power series, and using that, and, well, I mean, I guess you don't even need that because it's almost uniform, but that's one way you could do it. And so it turns out you can compute the other moments, and let me see. So you got the variance equals 2n over, sorry, that's an n squared over 3 plus 2n over 3. And then if you, so from now on, if you just compute the standardized centered moments, you get 0, 9 over 5, 0, 27 over 7, and so on. Okay? So if it's not clear what I just wrote down, like I said, that if you look at the sequence of moments, that's like a fingerprint for your random variable. So what I did here is, say, except for the expected value and variance, which I gave you formulas in terms of n, what I did for the other moments is I centered them, standardized them, and took the limit as n goes to infinity. So this is saying asymptotically, if I walk out really far, I'm getting the number of losing times as a random variable whose limiting distribution is something like this. Right?
So it's positive 3 over odd numbers?
Yeah, I guess, well, so, I mean, up to here it looks like that, yeah. So, I mean, I can compute more, so I'm not actually didn't check if that pattern goes on like that. But yeah. Okay. So any questions on that? Okay, so the reason I went back to this is just to show you, so in this case where you have your king go, where you can walk on the diagonal, then you can't do this. So you can't get the distribution in terms of that. Okay? Okay, so any questions yet? Okay, so what do we do in this case? So I'll show you over here. Okay, so in general, how to analyze the asymptotic behavior of random walls. Right, so in the symmetric case, we could get this sort of get the distribution in terms of n, but in general we can't do that. Even for the king case, which is really symmetric, we can't do that. Okay? So, so given a set S of steps, let W sub AB superscript S be the walks from 0, 0, so AB with steps in S. Okay, so for example, the royal paths thing, that was when S equals. So that was when S equals 1, 0, 0, 1, and 1, 1. Okay? So now I'm making it even more general. I'm saying, oh, what if we can step any way we want as long as there's actually some restrictions. So S has to always be going, generally to the right or up. Right? We can't be going backwards because then we just keep bouncing around. Okay? So we have general steps. Now how are we going to analyze this? Okay? So the ad hoc type of thing where we did for the king walk, and for the walk we just write in up steps, it's not going to work as far as I know if you just have a general set of steps, right? So what we're going to do